This is Keith Williams at UVA with an FEA analysis of a tuning fork. This particular old tuning fork rings at 128 Hertz. The length is about 10¼ inches. The arms have a width of about 5/16 of an inch. The tuning fork is made of aluminum, and the height is about 1/2 inch. These are the tools I used for this demo. I used Inventor Pro, just a simple desktop scanner, a meter stick, and I made this presentation with Sketchbook. Alright, the first thing is to take a scan of the tuning fork, which I did here, and then I imported a JPEG into Inventor Pro to use as a template. I'll just rotate that slightly just so that the arms of the tuning fork better match the Z-axis. This isn't really necessary, it's just something I wanted to do. Alright, so I'll use the rotate tool and just rotate my template image. That's about right. And now I have something that I can sketch on. So I'll continue my 2D sketch, just making the outer silhouette of this tuning fork. I'll be mostly using the rectangle tool. And I won't be relying on the scanned image for actual dimensions. I'm just using it to help me design. Alright, so the length is about 10¼ inches and about 1½ inches across, like so. Alright, and once I have that rectangle, then I can use the rectangle tool again to define the arms. As mentioned before, the arms are about 5/16 of an inch in width, and 5/16 is 0.3125. So I'll just sketch out the arms of the tuning fork like so. Same thing for the other arm. There we go. And now to make that half circle sort of cutaway on the interior of the tuning fork, I'll just use, it looks like the circle tool will work just fine there. So I'll just sketch out a circle and make sure that it intersects my rectangles. Alright, that looks about right. Now, those cutaways on the right-hand side really aren't necessary acoustically, but I'd like to make them anyway. I'll just use the spline tool for that. Remembering how the spline tool works. Oops, I messed up. That's alright. We can always undo and start again. Try that one more time. This almost makes me wish I had a 3D scanner, that I wouldn't have to do any of this. Ah, that's alright. Alright, almost finished. I'm not going to bother making the handle because that really doesn't play any acoustic role. All we're trying to do here is simulate the performance of this tuning fork. Alright, now we can use the trim tool to get rid of any extraneous lines. This is really pretty straightforward, but just notice that if you have dimensions attached to a line, then you can't simply trim away on it without causing all kinds of things to go wrong. So you have to remove the dimensions. You'll see a couple other examples of that. Once the dimensions are removed, then we can use the trim tool to get rid of extraneous lines. There we go, just about done. Just need to get rid of a few more. That line still has a dimension attached to it, so I'll need to get rid of that. Can't use the trim tool for that, of course. Okay, so once I'm out of the trim tool, oops, I'll just exit the trim tool. Now I can highlight it and just use delete. Get rid of that dimension and the lower one. Might as well go ahead and get rid of the length as well. And now just a bit more trimming and we're done. Zoom in and just make sure that all of our lines and curves are attached smoothly. There's one more line to trim out. There we go. All right, so now we have a two-dimensional silhouette of the tuning fork floating on top of a JPEG image of the scanned tuning fork. And we'd like to, I think it'd be a good idea to get rid of the image. We really don't need the image anymore, so we can click out the image in the history pane. And you might feel inclined to right-click on the image itself, but that won't help you. What you really need to do is go to the history pane, let's see, and right-click there, and then select visibility. Aha. So now you can just see the two-dimensional outline of the tuning fork just by itself. Let's rescale that and have a good look at it. Looks fine. Now we can extrude it. As mentioned, the height of the tuning fork is 1/2 inch. And there we go. Now we have a CADed tuning fork that matches the real thing. Well, not quite. We still need to make it aluminum. So what we can do is just assign that material. So I'll go to Tools and Materials and select Aluminum 6061. That should be fine. Doesn't really change the appearance much. But there you go. Now we have a FEA ready CAD model of an aluminum tuning fork. Now we can do the stress analysis. I'll create a study. We're not going to do a static analysis, but instead we're going to do a modal analysis. I'll unclick the number of modes and select a frequency range from 1 Hertz to, say, 500. I start at 1 just so I don't have to look at the 0 frequency modes, which are, of course, just translations. Don't really need those. And we can simulate this. Let that run. And look at our results. Very close. So we came within a few hertz of the correct answer. And we can animate that mode just for fun. Of course, the motions are greatly exaggerated in the animation, but it's still helpful. You might be curious what the higher frequency mode looks like. So let's click on that, and we can animate that one as well. This one you have to rotate sideways to see what it does. It almost looks like someone walking down the street, like with the legs moving, shuffling along. All right, so when you ring a tuning fork, you'll actually hear that sound as well. You may hear that sound as well, but the dominant sound will, of course, be from the lower frequency. Which is that mode right there. Okay, so this is a very, very handy tool. Suppose you needed to design a tuning fork of a particular frequency. You could do it in CAD. You could use the FEA to bring yourself very, very close to the desired frequency. And that would be a really, really handy tool. Okay, so I hope this was a helpful tutorial. Again, I'm Keith Williams at the University of Virginia School of Engineering and Applied Science. I hope you enjoyed this demo.